I've spent years homesteading in rural Michigan, gardening, canning, and raising chickens, with an internet connection beamed to our house from a grain silo down the road. For the past decade, I've spent every spring storm chasing on the cell phone deficient Great Plains of the United States, experiencing every data hole not shown in Verizon and AT&T's bullshit maps. My day job for the past 2 decades has been a network and communications engineer, specializing in voice and video over IP, and other forms of real-time communication. And last but not least, I'm an astrophotographer, and boy do I have some opinions about Starlink. As a hobby, astrophotography can kind of suck. There's a ton of gear involved. Setting up every night can drive someone mad, so much so that it could cause the more eccentric person to literally build a house for their telescope gear to live in. Winter nights way up north can make using a telescope a miserable experience. Yet in summer, the nights are very short. It can be very hard to make the most of them. If you are too far north, as in Alaska or northern Scandinavia, summer astrophotography is completely shut down. It never gets dark enough. Split the possible nights you can make these amazing pictures in half because of too much moonlight. Then, in many places, half of your nights could be ruined by clouds. Some seasons, like a Michigan or South Dakota winter, can be completely shut down by either clouds or high winds. You really can't operate from a large city, so over half the population needs to travel to get away from light pollution. The rest of us are seeing ever brighter outdoor lighting squeeze out the truly dark places on the planet. While taking these photos, random streaks of light from planes and satellites can pollute a photo, and if you are working with small, distant, and dim objects like galaxies, even Earth's apparently clear atmosphere can conspire against you with haze, scintillation, and air glow. It's almost a miracle anymore that photos like this can even happen at all. But to get one really important part of Starlink and OneWeb satellites out of the way, Starlink, or really any satellite in general, does not produce any sort of light at all. All of this light is reflected sunlight only. Calling a satellite light pollution is a bit of a stretch. We don't call the moon, a natural satellite, light pollution, but reflected sunlight from a large rocky body orbiting the Earth, even though that surface is almost as dark as charcoal. Objects we have put in space aren't natural, but the light they reflect is natural light. I'm making this point because it's important later. In order to evaluate Starlink's real impact on astrophotography, I need to clarify what kind. There are several kinds of astrophotography, a couple of which fall into the solar system object category. The sun, of course, is a star. Next, planetary, lunar, and solar photography. These are generally high magnification images of the lunar surface, Saturn, Jupiter, Mars, and Venus. And finally, near-Earth objects, asteroids, and bright comets. This category of solar system objects will likely never be impacted in any meaningful way by Starlink or any other future internet satellite constellation. These objects are far brighter or far too small to have satellites or planes or other objects crossing your shot. Individual exposures are very short and are more or less just like taking daytime or dusk pictures on Earth. But there are some problems with Starlink once we start talking about a different kind of astrophotography. Deep sky astrophotography has two main flavors, wide and narrow field. Wide field astrophotography includes shots of the Milky Way, zodiacal light, or entire constellations. Typically these are done with a standard camera, with a standard lens and long exposures, typically between 10 and 30 seconds. This type of deep sky astrophotography is within reach of almost anyone. And by the way, if you are interested in it, this is where you should start, long before you begin shopping for telescopes. Due to Earth's rotation, a camera on a tripod taking a picture with a longer exposure time reveals star trails, another kind of wide field astrophotography that many beginners and even experts alike love and try to experiment with. Another type of deep sky astrophotography is narrow field, or really anything that might involve a telephoto lens or a telescope. This is quite different from wide field. Target objects tend to take up very small areas of the sky. They are typically very dim, and it requires a tracking mount in order to correct for Earth's rotation. Because the sky itself, even the darkest of skies, have some sort of brightness, and because aforementioned objects might cross our field of view, we typically won't just do hours-long exposures to get results, but instead make sub-exposures, taking dozens or even hundreds of different long exposure photographs, and then averaging them together in software. These two types of astrophotography are where Starlink is going to cause some problems. Or, well, maybe. When I was 10 years old and attending a before-school astronomy program in elementary school, the teacher flipped on the TV to tell us an important and historic event that was taking place. A United States coalition had just launched a war with Iraq to free Kuwait from Saddam Hussein-led Iraqi occupation. But something here got my attention.
See that? Please update us. Do we have Charles? We're now told Go ahead.
We're now told it was a national air raid alarm. A national air raid alarm that did not affect the situation here right now.
We're going out to Charles Jaco in Saudi Arabia. He's in Dhahran. Charles?
Just lost the line.
We hear the sirens and we can see you,
Hello.
Charles.
This is Charles Jaco in Saudi Arabia. Right now, the air raid sirens are going off.
There was an interview with a reporter in the Middle East that just didn't seem natural. There was this enormous delay between when the studio reporter asked a question and when the field reporter answered. I had no idea why at the time, but soon, as the first Gulf War continued, I had learned about geosynchronous communication satellites.
Lining up shelter, they realize it may be the other shoe here.
I think, Brian, if you're still talking to me, the audio is intermittent here.
Mike Taibbi on the border between Iraq and Jordan, and our apologies for the communication difficulty and the combined maddeningly long satellite delays these days because of the pressure for satellite time, the overwhelming number of requests for it, and the narrow bandwidth, I'm told.
Satellites at just the right distance from Earth perpetually stay in the same location in the sky, way above the Earth's equator. Due to the limits of the speed of light, any communication done over this kind of satellite means that there's a quarter second of delay to get a transmission from one place on Earth to any other in just one direction, and another quarter second to get a response. The cumulative time is called round-trip time, or RTT, is in this case over half a second, and that's just ground to satellite, and doesn't include the time data, especially compressed video, is processed or transmitted across terrestrial networks. Humans can handle around 300 milliseconds, or that is to say about 0.3 of a second round-trip time before a phone call starts to feel unnatural. If you've ever attended a conference call and heard people talking over each other spontaneously, you'll probably know what that feels like. Geosynchronous satellite-based communication is more than twice as bad as that. For an internet connection like this, you can forget making phone calls, let alone gaming. Given the differences and limitations of fiber optics being laid down across vast oceans, one possible way to get around this communication RTT delay is to put a constellation of satellites into low Earth orbit, where the distances and RTT become much shorter. In the late 1990s, the Iridium constellation was born out of this idea. These were 95 satellites orbiting in different positions all over the globe that would allow short trips for voice communication from one part of the globe to another. The idea had a lot of promise. At the time, there was very little cell or no cell phone coverage in rural parts of the globe, and the idea was that people in remote locations could take advantage of this network to communicate with the outside world in an emergency or in critical situations, or even for daily business. However, the idea ultimately failed to be commercially successful. Cell phone networks quickly caught up in the 2000s. The emergence of broadband internet capabilities brought the suburbs and small communities high-speed connections to the internet, but that didn't solve everything. There still isn't a solution for truly remote applications. And just as bad, many places on this planet don't have competition to drive down costs or give people and businesses options to consider. Iridium was mostly just for voice communication. It can't deliver internet. It somehow managed to be too late for voice, but too early for internet connectivity. In spite of the failure of the first generation of Iridium, the network became somewhat famous among amateur stargazers and astrophotographers. Their very large solar panels would reflect enormous amounts of sunlight for a few seconds. The very bright flashes could be observed on the ground. They became known as iridium flares, resembling slow-moving meteor streaks. They were a novelty, a predictable one at that, one that someone might deliberately plan and photograph. They also frequently added to your meteor shower time-lapse or Milky Way photo. What the world really needs is a very low latency, high-speed, available anywhere, redundant connection to the internet. And to truly democratize access to the internet for the entire globe, it needs to be cheap too. Starlink will be a game changer, whether you are a farmer or off-grid, whether you chase storms on the plains, for those living in developing nations, oil and gas extraction, mining, military applications, adventure, field science. When a business needs a new internet pipe from their provider, or needs a second one from a competitor for redundancy, it can take months, sometimes up to a year, to get that last mile of fiber trenched to the building, even in larger cities. Starlink won't really have any setup time, even for small or large businesses. Redundancy and high availability for any business stuck without competitive options. For them, Starlink is a game changer. And this whole 5G thing, it's really only viable in high population density areas. Rural communities are once again left out of the equation. And then there's the big one, The Internet of Things.
Air travel, bus travel, school bus, freight systems, shipping, pipeline infrastructure, wildlife, heavy earthquake sensors, grain operations, electrical grid, disaster vending machines, cars, flood detection, street lights, data disaster harvesters, and national park systems.
The list of internet-connected devices that have come online or are coming online soon is endless, and I predict they'll all be served by solar-powered satellites. Not buried or aerial copper or fiber infrastructure, and far fewer repeaters, switches, and routers, all drawing power from the electrical grid 24/7 like today. Starlink and OneWeb may not just be your internet connection, it may become the internet as we know it in the future. The possibilities for telecom disruption in the next decade are mind-blowing.
But in order to get there, Starlink and its competition need to place an adequate number of satellites into orbit. And SpaceX, which until recently was only a prolific launch provider, is now its own biggest customer and the largest satellite operator in the world by quantity, and it's only just gotten started. To make sense of how and why Starlink is launched the way it is, let's play a little bit of Kerbal Space Program. Each Starlink launch places 60 260 kilogram satellites into orbit at one time. Each satellite is actually quite small in reality, but with 60 of them, it is very close to SpaceX Falcon 9's payload capacity when the first stage booster is recovered. Not only that, the launch completely fills the fairing of the Falcon 9 to capacity. After separating the first stage, which returns to Earth and lands on a barge, the second stage places the 60 satellites into orbit at a 53-degree angle relative to Earth's equator, then later corrects that orbit precisely with a quick 1-second burn. However, the satellites are now at only a 260-kilometer altitude above Earth. This is not a great place for a satellite to be, but in this case, it's a smart one. Officially, space begins at the Kármán line of 100 kilometers. But the effects of Earth's atmosphere extend much further than that, which will induce drag, slowing a satellite and causing it to come crashing through the atmosphere and burning up within just weeks. That's not a bad thing if one of your satellites goes rogue and can't be moved into its final orbit. And there's another problem to solve. All 60 of the satellites are packed very closely together just to fit into that Falcon 9 fairing. To solve this, SpaceX induces the second stage into a slow tumble using cold gas thrusters. This causes the outermost satellites to have the most angular momentum, while the inner satellites have less. By ejecting a few springs, the satellites pop away. Whoops. By ejecting a few springs, the satellites drift away from the second stage, each at slightly different velocities. The outer satellites will have an ever so slightly faster velocity than the inner ones, so they gently drift apart. And what started as just a few centimeters of spacing quickly increases to a kilometer, then dozens of kilometers over the course of a few days. During this time, the spacecraft orient themselves in such a way that their solar panels, which are deployed immediately to keep the onboard batteries charged, and their krypton-based electric ion engine ready to run. But it needs to be in a configuration that is tangential to the circumference of the Earth. That atmospheric drag would be too much if the solar panels were perpendicular to Earth, behaving like a sail, slowing the craft down and eventually deorbiting it. It's during this time, at very low altitude, and while the solar panels are parallel with the Earth, that Starlink appears exceptionally bright, exciting, alien, or even just off-putting to ground-based observers. As the satellites drift apart, these trains get longer and take more time to cross the sky. After a few days, satellite operators take control of the spacecraft's onboard thrusters and boost each satellite to their final orbits at 540 kilometers, almost double the height. Then, the solar panels are oriented to face the sun, not to the ground. The result of these two changes are far less reflective and a far dimmer satellite once in orbit, going from as bright as a magnitude 2 star, similar to the brightest stars in Orion, and bright enough to spot even at dusk, down to a magnitude 5, similar to stars so dim that you'll need to go to a national park, a dark sky site, or a very rural area away from city lights in order to even spot them. Similar to most of the stars in the Little Dipper, and that's during optimal conditions to try and see a Starlink satellite. Starlink is launched at the very limits of the Falcon 9 rocket to a minimal orbit. Then SpaceX boosts Starlink to a proper orbit. In order to be commercially viable, the first stage and fairing are recovered. The satellites themselves are mass-produced. Even the thrusters use cheaper noble gas, krypton, instead of xenon for orbital maneuvering, even if that gas isn't as dense or as powerful to use in an ion propulsion system. Cost is key, and every bit of power is squeezed out of the launch system. The name of the game here, in order to have so many satellites in orbit, is cheap and reliable. But as we all know, you can only have 2 of the 3 in the good, fast, cheap triangle. Getting Constellation online will take time, and 17 more launches are planned in 2020 alone, which will be just enough to start serving some customers at the end of the year. In a more recent launch, one Starlink satellite was coated with a special paint to make it less bright. But during the initial separation and Starlink train phase, it appeared to be no darker than its 59 sister satellites. That makes sense though. The spacecraft's body isn't the real problem. It's those flat, oriented solar panels that are the issue here. Once placed in final orbit, it's very likely the tinted satellite will appear darker. We'll have to see. So now that we know what Starlink is, how it gets there, and why it's so bright at first, let's talk about some deep sky astrophotography basics. Again, planetary or solar system photography isn't generally going to be affected in any meaningful way at this point. Deep sky and Milky Way photography is where things get dicey. At the most basic level, deep sky astrophotography is all about collecting the very dim light of stars, galaxies, and nebular clouds onto a piece of film or an image sensor, whether that's a dedicated astronomy camera or an off-the-shelf camera. It doesn't matter if we're talking about a lens, a backyard telescope, or an observatory behemoth. The name of the game is just about the same: collect light. Not in hundredths of a second, but measured in minutes, hours, even days worth of exposure time. For the most part, the more time you collect light, the better the image will be. But there's going to be some problems with that. Objects we don't want will cross the path of your lens or telescope in those timescales. Planes, stray lights, satellites, meteors. I even once had a Chinese lantern get in my way. Small clouds and haze might pass through. Airglow, zodiacal light, and light pollution eventually can add up and overwhelm an image and ruin it. Digital imaging sensors not only gather light, but pick up noise as well. Heat, non-visible light, electronic noise, background radiation, and other electromagnetic sources. The sensors themselves have flaws, like bias, hot pixels, and amp glow. And importantly, deep sky astrophotography needs to be performed when it is absolutely dark. No astronomical twilight should be around to invade your image, or you just won't get a great result. To solve some of those issues I mentioned, astrophotographers make sub-exposures and dither the image as it is collected. Suppose the goal was 3 hours worth of light to collect for an image of, let's say, Andromeda. Instead of one 3-hour exposure, perhaps it would be better to make 60 3-minute exposures. And for each picture, adjust the telescope ever so slightly so that different pixels can be responsible for collecting different parts of the image. After we've collected all of the subs, we can then combine them, correct for sensor noise, and remove extra gradients caused by an uneven sky or extra glow on the sensor itself, or even flaws in the whole imaging system. Pictures ruined completely by stray clouds or objects are removed from the stack, while some of the images with minor flaws stay put. These minor flaws can be rejected as noise by stacking algorithms, and that includes low-magnitude Starlink satellite passes. So let's actually address the hysteria over Starlink and other satellite constellations. The International Space Station, or ISS, when it makes a perfect pass over your location, is as bright as magnitude -2, or as bright as Venus. In fact, here is the ISS passing near Venus. But you'll notice I'm photographing the ISS at dusk. The sun had set just less than an hour ago. This isn't even after astronomical twilight. In other words, this isn't a good time to perform deep sky astrophotography. As the ISS passes directly overhead, it reaches its maximum brightness. This is when the ship is closest to you, and why it's the brightest during this pass. But in spite of how glaringly bright the ISS is, it continues to pass overhead, quickly dim, and suddenly disappear. It's gone.
And disappear. She's gone.
You can't see it. It's like it's not even there. So what happened? Satellites like Starlink and massive stations like the ISS, again, don't produce any light whatsoever. It is reflected sunlight alone, and that's it. What happened is, the ISS disappeared into Earth's shadow. To an astronaut on the ISS, the sun had just set behind the Earth. You see, after the sun sets, Earth's shadow is cast against the sky. As the sun sets deeper, the shadow can be seen to move up and overhead. This is called the belt of Venus, or Earth's shadow, cast on Earth's atmosphere. This shadow continues above the atmosphere until it's finally cast onto satellites in low Earth orbit. At this point, the sun is about 18 degrees below the horizon, and we are finally past astronomical twilight. The sky is at its darkest, and it's the time to begin most deep sky astrophotography sessions. Just like the ISS, Starlink satellites, or the Starlink train, disappear behind Earth's shadow, one by one. The streak they create in long exposure photographs completely fades away. Now, here's just a little anecdote. We've had 4 Starlink launches at the time this video was published, and all 4 times I've tried to catch the Starlink train at its brightest and closest, whether before dawn or after dusk, and this is the closest I got. Did you see it? Let me rewind. For all my efforts, this was the only pass I got, and you can barely see it. So let me make an interesting point. You need to go out of your way to catch a Starlink train in some cases. Having a few images of your astrophotography ruined by Starlink either requires effort, luck, or really poor planning. The reality for astronomers around the globe is that to capture a Starlink train, you'll have to be in the right place at the right time. Given enough launches and the number of observers, someone will have a noise complaint about Starlink for every single launch. While people like me, going out of my way to hope for a decent pass, can't seem to catch a really good one. It's a bit of a paradox. On top of that, avoiding astronomical twilight or the few minutes after isn't just a good idea anymore. It's imperative. But it seems like everywhere I go on the internet, it's as if the sky is falling.
Oh my god, that's weird. I cannot imagine thousands of those in the sky at the same time. It has now become even more terrifying than it already was. If that's the future of the night sky, if there's going to be thousands of those things up there for the sake of internet, oh man, I feel sick. I literally feel sick.
Take this example from spaceweather.com. I'm a big fan of this site, and have been for over 20 years. And this just has me shaking my head. This image of the Orion Nebula doesn't have Starlink satellites in it. These are satellites in geostationary orbit, satellites that do not move. And so while tracking stars in this region very close to the celestial equator, geosynchronous and geostationary satellites, like the ones you use for XM radio, DirecTV, or the GOES weather satellites, appear in astrophotos. These satellites are nearly always quite large and almost perpetually bathed in sunlight. How do I know this? I learned this from spaceweather.com 14 years ago.
Come on, man!
Or how about this video of the Alpha Monocertids photobombed by a Starlink train? While it does kind of stink that this happened, notice how it was just before dawn, and all the other meteor cameras, this being one of dozens of them around the planet, weren't affected. Sometimes it's just sexier to focus on the downsides, which admittedly do truly exist. And then there's the numbers.
20,000, 36,000, 52,000 satellites in total. The idea sounds like the sky would just be saturated with bright lights all dusk and dawn. But I also think the Starlink trains are really just giving a bad first impression. As the numbers go, I don't think it's going to be as bad as it sounds. Hear me out. These numbers are just slots approved by the FCC. Places to put satellites if they are needed. Emphasis on needed. As a network engineer, it would seem to me that if I was delivering a product to a customer in a greenfield scenario, the first concern is really just getting the network up. 1,000 or 1,500 or so satellites is probably going to be enough to get things going. And there would really be no reason to add more right away. At this part of the evolution of Starlink, there's going to have to be more demand before there are more satellites added. If Starlink satellites start to be oversubscribed over certain parts of the planet, Then it's time to add more satellites. Adding another 1,000 satellites would effectively double the amount of bandwidth. That would mean that Starlink hadn't iterated at all on the design of the satellite. It's very likely that the next generation of Starlink satellites would have more throughput on each satellite than the previous versions. In other words, each new iteration of Starlink should have more capacity than the batch prior. In 30 years, we've gone from 2 megabit per second BNC to 10 megabit Ethernet, then 100 meg, then 1 gigabit per second. And these days, businesses have multi-channel 10 gigabit networks like it was old hat. For LAN connectivity at least, that's a doubling of speed every 2 years for the past 30 years. The progress of Starlink will likely mirror this. And that doesn't even include the optimizations that have come along the way in those same 30 years. 30 years ago, 640 by 480 video required 60 megabits per second. 8K video, over 1,000 times the resolution, still only requires 60 megabits per second. In the future, we could see a scenario where doubling the amount of Starlink satellites could actually multiply the throughput by a factor of 10 rather than just double. In my opinion, and what I think the reality is that Starlink will never have 52,000 satellites. It may even have less than 20,000, perhaps even less than 10,000. We'll just have to wait and see. Those huge numbers, I think, are more about preparing for satellite replacement cycles, planning for the distant future, and grabbing orbital slots before competitors do. Not about planned or expected capacity concerns in the near future or in the short term.
But it's not all sunshine, roses, and high-speed broadband on your catamaran. Do you remember seeing this image from 2019 that shook up the astronomy community? It's a black hole, directly imaged for the first time. It took the effort of 8 observatories around the world. But here's a little-known fact behind the image. Each participating observatory had to ship physical hard drives from all over the world to a central processing location at MIT, who would be responsible for processing the final images. One of those observatories, the South Pole Telescope, was physically closed to access for the winter, and so there was a 7-month delay transferring the data by plane to MIT, where the data could finally be processed. Why hard drives over the FedEx sneakernet?
Well, how exactly do you get high-speed data up to places like Mauna Kea, Kitt Peak, or the Chilean Southern Observatory, let alone an internet connection fast enough to move terabytes of data? And they can't just shut down all other science operations while they try to send one experiment. These are remotely operated observatories. It's a hard problem. And each time these observatories need to upgrade their ground-based internet, it means trenching fiber optic cables up the sides of mountains, in the middle of nowhere, or even the frickin' South Pole.
Perhaps Starlink to the rescue. Not only is it now feasible to have high-speed links to existing observatories, the logistics of putting an observatory anywhere on the planet is now streamlined, even for amateurs. It's true, there are literally communities of private observatories in more eccentric corners of this planet. Starlink and OneWeb could lighten the blow to some forms of astronomy by offering observatories reduced rates, high throughput by shotgunning multiple satellites, or even prioritized bandwidth. After all, most of these observatories are in remote locations without much bandwidth competition. As the Event Horizon Telescope expands and ever larger telescopes are brought online, even larger amounts of data will need to be moved. And these internet constellations could be a great way to reduce costs and increase science output. Starlink trains, before the satellites are boosted, are the most problematic time for deep sky astrophotography, and may take some planning to avoid them. Or in my case, just good luck, I suppose? SpaceX is working with the American Astronomical Society to come up with solutions to avoid Starlink satellites from being too bright once in their final orbits. This is good news.
Elon Musk himself has stated that he has no intention of ruining ground-based astronomy. The astronomy community will hold him, his companies, as well as Amazon and OneWeb to their word.
A lot of new satellites in orbit could create some interesting phenomenon and interference. Wide-field Milky Way astrophotography is, for the most part, juxtaposing the night sky against your favorite terrestrial objects, or just gorgeous scenery. Normally I would say the same things. Avoid Starlink trains, avoid astronomical twilight. But if you're planning on taking your photograph around 53 degrees north or south latitude, you might have a bad time. In fact, it might even be a bit of a problem for normal deep sky astrophotography as well. You see, most of the Starlink constellation currently planned will crisscross the night sky near 53 degrees north. This is close to places like York, London, Oslo, Moscow, Winnipeg, and Edmonton. Close to the summer solstice, areas of the world near this latitude experience only fleeting moments outside of astronomical twilight. In other words, you may never escape the glow of satellites, both current and planned like Starlink. While this is already a problem, Starlink is about to make this incredibly worse. It's not the brightness of Starlink in this case, it's the density. Even at dim magnitude 5 or less, dozens, or in the future, hundreds of satellites will be crisscrossing each other directly overhead of these cities near 53 degrees north. In the summer, they will be visible all night long. Taking Milky Way wide-field photographs are certain to be photobombed by ever more satellites, including constellations like Starlink.
I feel sick. I literally feel sick.
But I'm going to turn this on its head a bit. We have to admit, astrophotography close to the summer solstice is difficult already due to the extreme short length of night. It would be far better to just wait until August or September to capture these same targets, earlier in the evening and during a wide window to record them. Weather patterns at these latitudes rarely afford cloudless night skies in late spring anyway. But what if satellite tourism was a thing? Perhaps the kaleidoscopic patterns traced by these satellites might actually become a photography target themselves. I guess we'll have to wait and see.
The real tragedy here might actually be radio astronomy. I'll link to Fraser Cain's video in the corner here. This is where I think there will be some serious losses. While Starlink satellites do disappear behind Earth's shadow, they are, by their nature, radios. Detecting and experimenting with deep space radio sources, whether natural or hypothetically intelligent, is going to be a lot harder. Today, these internet satellites don't shut down during any part of their orbit. There are definitely other areas of astronomy that are going to be affected. Check out Fraser's video if that interests you.
SpaceX is currently working on the Starship program, a 100% reusable satellite and people ferry. Starship is capable of 100,000 kilograms of payload to low Earth orbit, reusable, compared to Falcon 9's 16,000 kilograms. For SpaceX, it means it may be technically possible to launch up to 1,500 Starlink satellites in just one go. Imagine a Starlink train up to 25 times as numerous and as long. But that's only half the equation. Starship can launch these satellites, not to 260 kilometers altitude initially, but directly to the final orbit of 500 kilometers. It has the delta V to do this, even when fully loaded by Starlink. Even better, this altitude would mean Starlink never needs to be in low drag configuration. By then, the hope is that the satellite's albedo has been reduced as well. The idea here is that SpaceX's next generation launcher will not only avoid the loud and bright Starlink train we've seen so far, save energy on krypton gas to increase Starlink's longevity, reduce the frequency of the launches, they'll interfere less with astrophotography up to that point, at least in theory. On the point of radio astronomy, there are places on Earth that are really not important to provide internet services, whether that's for legal reasons or because there simply isn't any demand whatsoever. Like say the southeastern Pacific Ocean. What if SpaceX were to turn down Starlink's radio signals over certain parts of the globe? This could allow for interesting niches around the planet where ground-based radio astronomy could be perfectly viable into the future. Many satellites and space junk in orbit today, of the thousands in place, could simply be deorbited and eliminated from the night sky due to redundancy and obsolescence. A future Starlink or OneWeb-like constellation could easily replace existing constellations, even GPS, and any geostationary carriers in orbit. This might actually reduce the overall radio noise coming from space from some signal bands, and make filtering out noisy internet constellations just a little bit easier. The Starship program itself could be a great way to do some low Earth orbit housekeeping. By being reusable and refueling on orbit, space debris and defunct satellites could be cheaply removed from the night sky. And for the ultimate Starship ace in the hole, 9-meter wide telescopes in orbit, or even bigger ones if they fold them up like James Webb. Space-based astronomy is about to get a lower cost advantage to lifting astronomy hardware into orbit or even beyond.
This is definitely not a sky is falling or filling scenario for astrophotographers. The Starlink trains are quite avoidable, they're predictable, and they can be canceled out in images using software. They may even go away in just a year or two. Radio astronomy isn't completely doomed so long as satellite operators are willing to work with astronomers. However, there are some problems that seem completely unavoidable right now, like far northern latitudes in summer, low brightness passes of just way too many satellites. I'm optimistic that not only will we avoid ruining astrophotography, but that we can actually work with these internet constellations to enhance ground-based astronomy. And while right now this might be a bit of a stretch, I'm thinking we can even create safe zones where astronomy can continue even less impeded than it is today. Thank you for watching, and I hope you enjoyed that video and learned something new and interesting today. If you did, you know what to do.